The first speaker is Felix Queißner. Felix lives in Germany, near Stuttgart, and he's a modern rebel. If you live near Stuttgart, you have to work for either a car company or one of the companies that work for car companies, like Bosch or Siemens. He's one of the few that works for neither, and when people asked him AMD or Intel, he chose an FPGA board instead. The talk is SPU Mark II, or How I Stopped Worrying and Coded My Own Toolchain. Felix, the stream is yours.
Yeah, hello. Loris introduced my stream title as well, so I can now continue to the next slide already. Who am I? Loris introduced myself a bit. So I'm a full stack developer by day. I create desktop applications for our in-house use, like testing systems and so on. And I'm a crazy scientist by night, like introducing new programming languages, inventing stuff, building hardware, and building a computer. I love low-level programming systems. I love like old computers, retro computers. And my programming career started in game development, focusing on graphics. So one led to another, and now I'm a demo coder and doing low-level crazy stuff. I'm going to talk about my grand project, which is designing an own CPU architecture, as well as designing a whole computer around that. I started designing the SPU Mark II architecture in 2017, and as you can probably tell from the Mark II, it's my second version of the same architecture. And yeah, it's 2020 now, and it's time to build a computer around it, as the CPU architecture is ready to use. And thus, the Azure Home Computer was born. The Azure Home Computer is inspired by the late 80s home computers like the Amiga 500 or probably the early as well, like the C64, so Commodore inspired. It uses the 16-bit CPU with a 24-bit memory bus, so it has an MMU. It has a VGA output for graphics, and it has serial port I/O. There are different features planned for the future, like having an SD card interface or a keyboard attached, so you can actually work on it like a really new computer. And yeah, that's a photo of the computer. I can zoom in a bit so you can see more. We have on the left a VGA screen displaying a wonderful screenshot of Commander Keen. And it's actually rendered by the FPGA board, which is the thing with the blue LED glowing. And we have a RAM connected to that, and we have a small like VGA graphics card dish thing, which is actually just a bunch of resistors doing analog digital conversion. So yeah, what are the bigger problems when you design your own computer? Well, first, CPU design is hard. You can see that like Intel is doing it for years and they still have bugs and complicated stuff in their CPUs. And the CPUs are humongous things of silicon, which do awesome computing stuff. And well, I started designing my CPU architecture in 2017, and now it's 2020. 3 years later, I'm actually ready to start building a computer around that. Why is that? Well, designing like a fantasy console is one thing, but having something that is working in hardware or even is remotely usable for a long-term computation stuff is hard. And yeah, the other problem is having no toolchain means you have to use a hex editor and you have to use a lot of paper to actually assemble your code from a text representation into binary representation. And Zig helped me solving this problem by creating a whole toolchain for that. I have a debugging tool which is similar to GDB. It can halt the CPU, it can single step, I can peek and poke stuff into memory. I can enable or disable components of my computer at runtime. It's quite usable. I have an emulator, which is crucial to implement your programs, because Right now, flashing my computer takes about 30 minutes per cycle, so iteration time is really slow if you want to test stuff on hardware, and testing stuff in an emulator helps a lot with increasing your productivity. Also, having an assembler is crucial to not doing a lot of paperwork. It helps me assemble my code, and it helps me being productive as well. And this is what this talk is about, how did I write my own assembler? I also have a disassembler, which isn't really good, but it works enough to see if the assembler did its job. And now I can trust my assembler to just do what it's supposed to do. And there are also a couple of helper tools in my tool chain that convert Intel hex files to binary files, that convert binary files then to VHDL files to be able to compile that for the FPGA and so on. And yeah. Now, to give you a small context about how my assembler language actually looks, it looks like this. We have comments, like in most assembly languages, introduced by a semicolon. We have directives to the assembler, which can relocate code, which can insert data, and we have instructions. And my instructions have a small thing called modifiers, which are these things in square brackets. I'm going to talk a bit later what those actually do, because it's really special to my CPU architecture. And yeah, I have more directives, which is alignment, which inserting strings with zero termination, and so on. It's a full-featured assembler you can work with. And yeah, what does an assembler do? It takes this code and turns it into a binary, which looks like this. You can see that, well, this isn't really readable. We can see, hey, we have hello and we have world, which is the string from the previous slide here. And we can now look what the assembler did out of our push app message. This gets assembled into the push instruction, which is 0801, and followed by A1A80. The address of the hello world message here is 801A, which is, as the code is offsetted to 8000, is 18191A0D is the carriage return here. And this corresponds to our app message label down below. So what feature requirements do I have for an assembler to be usable? Well, the first one is assemble code, and that's the most basic feature you want to have, because without that, it's not an assembler. The second point is I wanted to have include files that allow me to share data or code snippets between different projects or programs. Like my BIOS is having a huge table of entry points into the BIOS and magic constants. You can see them here. For example, app start is a constant that is referring to OX800, which is the entry point of programs in my computer. It should allow arithmetic expressions, like 1 plus 2 is an arithmetic expression, and it's not perfectly trivial to evaluate these, but it's also not hard. Then I need to embed binary data, which is including an image, or in Zig, at embed file. So I can include data pre-computed, like sign tables, images, also bigger text files, to just don't have them to code manually by, oh yeah, this byte and then this byte and then the next byte. This is not convenient. And another quality of life feature is parser recovery or multiple error messages. Zig has this for I think, a month now or 2 months, like where the parser doesn't error out on the first syntax error. And it's also a huge quality of life improvement to have several parser files, parser errors, instead of just erroring out on the first, then you recompile and you see, oh, well, my next line has a syntax error as well. It's not convenient. And to talk a bit about assembling itself, what is assembling? It's turning text, which is the assembly language, into the binary, which is the machine language. I showed you before we have an assembler file and we have a machine language hex dump, and that's actually the job of an assembler. And it also provides us with stuff like symbols, for example, with labels, instead of hard coding numbers in the code like I did before without my assembler. And that makes the code portable. That means it's not portable between platforms, but between memory locations. As soon as I insert an instruction into my code, every code after that is shifted in memory, which means, well, I have to recompute all addresses there, and an assembler is doing that for me. I'm also going to talk now a bit about instruction set architectures and how they differ. First, instructions are encoded in memory, like you need to tell the CPU what to do. And instructions have usually like at least 2 components, which are the instruction itself or the opcode. It's to tell the CPU, please add stuff, and the operands tell the CPU what to add. And some architectures, as far as I know, ARM and the Parallax Propeller architecture have conditional instructions, which means please execute this instruction only if a comparison was 0 or was overflowing or something. And somehow this data must be encoded in a binary to tell the CPU. And instruction architectures also differ in the encoding length of instructions. x86, for example, uses a variable length instruction set, which means instructions can range from 1 byte length to, I think the biggest is something about 60 bytes. You can have really huge instructions on x86, or you have fixed length instructions on ARM, which are 32-bit per instruction, and that's fixed for all instructions. All instructions are the same size. Fixed length instruction sets make decoding easy. Like, you want to get the next instruction, just add 4 to the instruction pointer and you're done. For variable length instructions, you have to actually decode the instructions to get the start of the next instruction. For an assembler, however, it's irrelevant if you use fixed length or variable length instructions, because the assembler emits them anyways, like from front to back. And my own CPU has a variable length instruction set, which is highly orthogonal. What does orthogonal mean in this case? Most instruction sets allow you to use some portions of register sets or addressing modes on some instructions, which means if you can do A with B, that doesn't mean you can do A with C, and that's making assembler coding a bit harder, because you have to think about if that instruction is actually allowed or not. And an orthogonal instruction set allows you to do everything with every instruction. And the SPU has one kind of instruction decoding, so every instruction is decoded and executed in the same way. And the decoding part is actually one of the things that makes the CPU special. And there is one field in the instruction set, which is like the command field. You can see that below here, which actually defines what the CPU does to your data. And everything else in my instruction table here is like the executional conditional, the input 0, input 1, flag modification, output everything is the same for every instruction you can do. And only the command will differ for the CPU itself. So commands define what to do with the data you provide, which is like add or load data. Execution conditional means every instruction on the SPU is conditional. There isn't a conditional jump special instruction like on the Z80 or x86. Every instruction is conditional. You want a jump, you make that jump conditional. Instructions take 1, 0, 1, or 2 inputs, which you can configure with the input 0 and input 1 behavior. And that means you get your command down below gets 2 inputs like arguments in Zig or other programming languages, and they return a value which is then modified by the CPU or processed by the CPU, it's defined how to process that return value by the output behavior. And here's another special thing. The output behavior has 2 major operations. One is push the data, which means you push the result of a computation to the stack, or you can jump to the result, which means the SPU doesn't actually have jump instructions. Every instruction is able to jump, and that's also unusual. And the last thing is the flag modification behavior, which means you have instructions like subtract, which can also modify the flags in terms of this, and you now can compare data with subtract. Yeah. So how does this look in Zig? Zig is quite helpful in doing low-level coding because we can just take the table and put it into a Zig data type, which is here a packed struct. We have the condition, which is the execution behavior. We have input 1 and input 0. And we have the modify flags, which is a bool. We have the output, which is an enumeration. And we have the command, which is also an enumeration. Using a tagged enumeration here is useful because we can tag it with a U2 type. So the input behavior here is 2-bit, and the input behavior here is also 2-bit, which we can see those are 2-bit types. And yes, that's just like it was hard in Z to make that portable and usable, and in Zig I just defined the struct and I was finished with all instruction decoding for the assembler or for the emulator and the whole tool chain. And it's really convenient. And now how does an assembler work? Well, first it's a tool that takes text and converts that to a stream of bytes. Every instruction read is appended to a stream of bytes and it's outputted instantly. Which means I read an instruction, I translate the instruction, I emit the instruction, and I repeat that cycle until I'm at the end of the file. And that process is append only, so I cannot go back and insert data which moves all other data, because then I will mess up my internal instructions and offsets. And we have one problem with that, which is forward references, which means what is happening when I'm doing a jump forward in code, like jumping from the main function into a sub function, and the sub function is in memory behind the main function. When I'm assembling, I keep references like symbols to stuff, and if I encounter such a symbol when assembling and I don't know it, I have no idea how to resolve this at a moment. So the solution to that is you have either a 2-pass assembler, which is pretty much we read the whole file and we decode it and we store all symbols. Then we go back to the beginning of the file and we start encoding the whole stuff again, and now we know all positions of the symbols. or we're going to use a patch list, which is, oh, I have found a symbol and I'm now going to insert that into the patch list, and I will resolve that later when I know the symbol itself. And what problems did I have with the assembler? I have code with holes, which means I'm having code starting at 0 address, and I have code starting at 0x8000, which means like the half of the memory, and there's 32K of memory in between. And yeah, how do you solve this? The other problem I had was how to solve arithmetic expressions. I talked a bit earlier about it, that it's not that easy, but it's also not that hard, and I'm going to tell you how to solve this. The other problem every assembler has is the forward references, which I explained already a bit. And a problem with my CPU architecture is the too many instructions problem. And I'm going to tell you about that also. So how to solve the empty space or the holes in the data stream. And that is done by sections. It's not like the sections you know from ELF files, which is like .data or .text, but sections are substreams of data in the assembler itself. And a section has an offset in memory and then just a bunch of bytes behind that offset storing the data that was assembled. .org is a directive to the assembler that creates a new section, and every time you write a .org, I'm creating a new section, appending that to a linked list of sections, and start assembling into the new section I created. Which means, in the end, I have a lot of sections. Some of them are empty, and all empty sections can be dropped. And I have like a sparse memory map of the stuff I wanted to assemble. Arithmetic can be solved by the shunting yard algorithm, which is, as far as I know, invented by Dijkstra. He's also the guy who made like this famous pathfinding algorithm. And shunting yard algorithm is really easy to implement. You just need a stack of values and you have an output stream, and the algorithm itself is explained on Wikipedia pretty good. So just look it up. It's a nice thing to know and to implement in your own project. It's a good exercise. One problem with shunting yard, though, is that it doesn't really do syntax checking. So you can just write pretty much any sequence of symbols and it will just take it and transform it into something that is roughly right or not if it's not syntactically correct. But for me, that was okay. It's an assembler mainly for myself, so I can live with that. My solution to forward references is the patching, and I explained earlier how that works. We had two-pass assemblers in the past a lot, and two-pass assemblers were used because we couldn't have the whole program in memory while assembling the whole program. Which means if we have a machine with 64K RAM, we cannot assemble a program which is 64K byte large. But on a modern machine, like anything built after, I think, 1995 or something, we can just ignore that problem and store the whole memory in RAM. So patching is way easier to implement, and it's also faster in execution. And how to implement it is you have your section list and you have a list of patches per section. And the patch is storing the offset where to patch your binary later and the expression that needs to be patched. So when you encounter an expression while assembling and you cannot resolve a symbol in that expression, you just put that expression and the offset where it should be put into a patch list, and you write bogus data, like I think I'm using AAAA in hex to just note that there is something wrong. And at the end of the assembling process, you just resolve that list, meaning you go to the list, you resolve every expression again that wasn't resolved before, and you write the data into at the position which you stored, or you do an error if it's not resolvable in the end. And on a problem on my CPU, it appeared to me that having an assembler is easy, but then I noticed that I have 32K possible instructions on my CPU, and you cannot remember that much instructions in any way. And my thought initially was to like make instructions with the same prefix, which means for every command I have, which would divide the set by 32. And well, it still yielded 1K instructions per command, and that's just too much. And my solution to that is those particles, which are the modifiers, I call them, this. And it allows you to change bit fields. So we have this structure, and each modifier is able to change one of these fields in the assembler. So we have an instruction add, and we want to override the input 1 field, and we just use the square brackets. We use I1 to mark the input 1 modifier, and we use peak to set that field to peak. And now we get an instruction which does input 0 is pop 1, input 1 is peak 1, then this instruction adds them and pushes the result. And it's really unusual to work with this, and assembler coders are, I think, a bit disoriented at first when they see this, because it's really uncommon to have this, but I don't see a better solution to this problem. And it reduces the whole problem space to 54 modifiers and a handful of predefined mnemonics like the add, which usually pops 2 values, adds them, and pushes the result. And now I'm going to show you how the usual workflow with the assembler itself works. And this is a small program which Loris inspired me to create. We have the org, we have some setup here, and we have an implementation of a C function down below. And this is how the assembler looks. And we can now use the Zig build toolchain to assemble the file. We can now look into our result, which is the Intel hex file. This is the output of the assembler. And we can put that into the emulator and run that, and it creates a beautiful maze. Yeah. How the code in the assembler itself looks, I want to show you some highlights. The code itself is like 2,000 lines of code, and I don't want to walk you through all of that, but the basic process. We create.
Felix, if you can see if you can increase the font size a little bit.
Oh, yeah, I'm going to try. Yeah. Okay. So we have the assembler object itself, which is a Zig struct, which keeps track of all assembling stuff and does some bookkeeping. I'm going through all files passed on the command line and pass those files to the assembler using an instream, which allows us to call this function recursively to allow the include files. And after processing all files, I'm going to use the finalize function, which applies the patch list we built. Then if we had any errors, we are going to return these. And otherwise, we're going to write a Intel hex file to the output, and we're happy. And two things I want to show. One for understanding the assembler is the finalize function, which goes through the, I think it's a hash map. No, it's a linked list here. And it goes through the linked list of sections, goes through the patches per section we have, and it will now evaluate expressions. Either it will create a missing identifier, that means we cannot resolve that patch list, or we're going to have a value here, and we're going to patch the value just right into the memory, which is done with that. And another thing is an elegant solution made possible with Zig. We can use structs and comp time to iterate over struct fields, and I used that to create my directive parsing. So the parser of the assembler, as soon as it finds something that starts with dot, it searches in the directive struct for a function called dot symbol, and it calls that function to parse that special directive. In this case, I'm having the function that parses the org, which creates a new section. I have a function that parses the .ASCII, which creates a string and emits that in memory, and so on. And using that is pretty easy in Zig. We have we encountered a directive, and now I'm going to iterate over all my function declarations in directives and call that function here. And I think that's pretty neat and a nice solution possible in Zig, because the comp time reflection makes it a lot more easy than before in the C++ assembler I built, which was horrible. And this assembler is actually quite clean and expandable. And yeah, a short summary of the talk is building a computer is hard. Really, you have to think about a lot of stuff. You have to know a lot. And I learned really much starting to build the ASHET. What I also learned is building a toolchain with Zig is not hard. The emulator is, I think, 300 lines of code, and I wrote it in about an hour. And I really think I wasted hours in writing the assembler in the emulator in C, because it is hard to handle overflows correctly. It is hard to handle everything in C is more complex than using it in Zig. And what I also learned is write expressive code and write code that is simple. And you've seen that we have a function called .org, and we can just call it to parse the .org directive, and it's clear what this function is supposed to do. And also build the tools we need. Zig allows us to build a lot of tools. It allows us to build fast tools, and I'm really happy with that. Yeah. If you want to know more about my project, visit ashet.computer for more information. There's also an online emulator you can use, and you can get the whole toolchain and source code for the project there. Yeah, thanks for listening.
Thank you very much, Felix. That was an awesome presentation. So let's move to the Q&A now. Just a reminder, to ask a question to Felix, remember to tag me in the chat message. And don't forget that I'm looking not only at Twitch chat, but also Discord and the Zig RC channel on Freenode. So each of those places is fine. So let's now move to the Q&A view. Okay, so Felix, while people think what they want to ask, let's start with the most basic question. How did you discover Zig?
I was ranting about C++ with a friend of mine, and he was like, hey, by the way, I've discovered this new language. It's called Zig. and look it up. It may be something for you. And he was right. And I started reading the spec, and I immediately fell in love with the language.
Okay. Wow. So a friend recommendation and you took a chance.
Yeah.
I see.
Exactly.
I see. How long ago was this?
I think it was last spring. So 1 year ago, roughly.
Okay. Okay, cool. So, by the way, another question that I had in my mind, the maze was really nice.
Thanks.
Yeah. So I saw that the C function that you pointed out that you had translated, the source shift, that's basically your
that's
pseudo
the random
random.
generator.
Yeah. Maybe let me take a look at it a little bit again. I'm going back to the first view so that you can share your screen. Okay, so it's very simple. It's just shifting.
It's
around.
shifting and doing XOR, which is like the name of the function.
Okay. And you're just seeding it at 1.
Yeah.
Okay, that's cool.
It's actually taken straight from Wikipedia, and I translated it to my own assembler language, and yeah.
Mm-hmm. So there is one question on Twitch from Rust Compiler. So the Rust Compiler is asking, why should someone switch or write a new project in Zig? Well, what are the main benefits over C++ and Rust?
For me, it's simplicity, and that is like shown in all the code. And you just go and you write your stuff, and it usually works pretty fast. And I used to write programs in Rust or C++ too, but I spent way too much time thinking about how to implement something instead of just doing it. And in Zig, the path is clearer because there's no like super high level abstractions, and you can just go the direct way instead of thinking which abstraction do I choose, how do I structure my classes, and you just go for the code, and it works usually, and it works pretty stable. And yeah, that's the point for me why I switched to Zig. It allows me to work roughly 3 to 5 times the speed like in C++.
Mm-hmm. When are you going to introduce Zig to your company?
Pretty much at 1.0. I've talked about Zig with colleagues already, and I said, yeah, I'm really going to push that when 1.0 is out, because every one of you will love this. They're all C programmers, not like C++ programmers, and they're all like, oh man, this undefined behavior stuff is hard, and we know so less about it. And yeah, and I think Zig will help there as well.
Okay. Let's see. We have another question. What does it mean to assemble hardware and toolchain for it? Is it on the same level of what Intel or AMD does?
Well, basically, I'm using the same processes as them, but at much lower level, because my CPU architecture is simple. It has less bits. It has no pipeline. It has no caches. It doesn't have the complex stuff. But as far as I know, the processes I'm using, like using FPGA to simulate and using self-written tools, is the same as they do, just on a not that complex level.
Okay, a bit of a joke question. What's the status with Spectre and other vulnerabilities with your CPU?
Yeah, I don't have them. My CPU doesn't have like those weird vulnerabilities because I don't have the features that enable them. So go with the SPU Mark II. It doesn't have Spectre. It doesn't have Meltdown. It doesn't have cache misses because there's no cache.
Nice. If there's any cloud provider that's listening to this talk, I'm sure they will make sure to contact you, and you'll probably get a multi-billion-dollar contract with them for sure. Another question, this one from chat. What would you like to see implemented or added to Zig before it hits 1.0?
Well, for me, it's probably both issue 1717, the function syntax unification, as well as the packed struct fixes, which I hope will come with stage 2 soonish.
Mm-hmm. Okay.
And yeah, otherwise I'm really happy with the language in status quo.
Okay. Cool. I think we got all the questions. That was pretty cool. Can you show one last time the maze?
Yeah, sure.
Let me transition first.
Oh yeah. One problem with my emulator, I cannot stop it when it runs and it doesn't do keyboard input. Yeah, it's using raw keyboard input instead of cooked keyboard input, and that means Control-C isn't going to break the process, but it's just inputting the ASCII character 3.
Mm-hmm.
And that means I have to kill the process from outside. But yeah, here comes the maze.
Nice. And is the printing speed, like, are you sleeping, or is that the emulation speed?
There is actually a pretty heavy idle loop in here, which waits 16,000 cycles.
Okay.
So if I remove that, we can just reassemble the code.
Can you also seed it to another seed?
Run it, which is done.
Can you also seed it to something else, like 42?
Yeah, sure. We can like seed. I'm preheating, so we can preheat it to 42. And assemble, run, and we have another maze.
Nice. Okay, thank you. That was awesome. So let's... Yeah?
You're welcome.
Okay, thank you very much. We can now move to the break.